In this video, we analyzed a double sideband modulation when the modulating signal is a random signal. In this case, the statistical model for the modulating signal is an stationary random process, zero mean and with known autocorrelation function, power spectral density, and power. The statistical model for the modulated signal is a random process S of t, where the analytical expression is the analytical expression corresponding to a double sideband modulation, the product between the modulating signal m of t and the carrier. Now we compute the mean of this random process. The mean of a random process is equal to the mathematical expectation of the analytical expression of this process. The cosine is deterministic, is out of the mathematical expectation, and here we have the mathematical expectation of random process m. This is the mean of the random process, which is 0. Therefore, the mean of a double sideband modulation is 0. Now we have the autocorrelation function evaluated at two instants, t plus tau and t, and the definition is the mathematical expectation of the product of the random process in these two instants, in t plus tau and t. The two cosines, the cosine at t plus tau and the cosine at t, can go out of the mathematical expectation. In the mathematical expectation, we have the definition of the autocorrelation function of m, expected value of the product of m at two different discrete instants, at two different time instants, t plus tau and t. We have an stationary random process, therefore the autocorrelation depends only on the separation between these two instants, which is tau. If now we use this very well-known trigonometric identity for the product of a couple of cosines, basically we have 1/2 cosine of the difference of the arguments. This is one argument, this is the other one. The difference is omega c times tau, and 1/2 times a cosine of the addition of these two arguments, and the addition of these two arguments is omega c times 2 times t plus tau plus 2 times the phase phi c. With this mean and this autocorrelation function, we can see that although the mean is constant, is 0, doesn't depend on the time, the autocorrelation function depends on the time, but depends cyclically on the time with a given period that is given by 2 times the carrier frequency. Therefore, we have a cyclostationary random process. For cyclostationary random processes, it is necessary to compute the time average of the autocorrelation function to obtain the power spectral density by means of the Fourier transform. Here we need to have the integral in one period of the time autocorrelation function. In this time autocorrelation function, we have two terms. With this common factor, we have this cosine of omega c times tau. This term doesn't depend on the time, so the time average is the term itself. And then we have the second term, this cosine over here, when we have the dependence with t. But taking into account that we have the integral in one period, the integral in an integer number of periods of a sinusoid, in this case this cosine is 0, therefore we can remove this term in the time average of the autocorrelation function, and we have only the first term. This is the result that we finally obtain for this time average. And then the power spectral density is just given by the Fourier transform of this term. Here we have the product of the autocorrelation with a cosine. The Fourier transform of the autocorrelation is the power spectral density of m, and the product in the time domain with a cosine produces two shifted replicas of the frequency response, in this case of the power spectral density. One is shifted omega c and the other one is shifted minus omega c, and each shifted replica has a scaling factor equal to 1/2. That this halves is 1/4 of the squared value of the of the carrier amplitude. For a cyclostationary random process, the power of this process can be obtained by evaluating at zero the time average of the autocorrelation function. Cosine at zero is 1, and the evaluation for an stationary random process, the evaluation of the autocorrelation function at zero provides the power of this random process. In this case, the power of the modulating signal M. And therefore, here we have that the power of a double sideband modulation is just half of the square of the carrier amplitude times the power of the modulating signal. Here, it's interesting to remark that this term is the term of the double sideband modulation. Here, we don't have power wasted in the transmission of a carrier, and as it happens in an amplitude modulation, in a conventional amplitude modulation. As in a conventional AM modulation, for the double sideband modulation, the bandwidth is twice the bandwidth of the modulating signal, because the shifted replicas of the power spectral density of M will produce twice the bandwidth of the modulating signal. For instance, if this is the power spectral density of the modulating signal, we have a shifted version here and another shifted version here of this power spectral density with this scaling factor, and it is very simple to see that here the bandwidth is 2 times the bandwidth that we have for the modulating signal. And this happens independently of the shape of the power spectral density of the modulating signal. Here we have another example of the modulating signal with a given bandwidth W radians per second. The shifted replica here has a bandwidth 2 times W, twice the bandwidth of the modulating signal.